Hello, everyone. So my internship project is privacy preserving patient linkage based on the secure multi-party computing. My name is Chen Hong Wang from Syracuse University, currently Master of Science student in Computer Science. And here's my mentors, Dr. Wang, Dr. Chen, and Dr. Jiang. And we start at the motivations. We know that the patients may receive healthy care at different institutions now, and nowadays the electronic or healthy records are widely used in the clinics. So the physicians or researchers want to accurate their diagnosis. They tend to have increased interest in secure and efficient data linkage for the cross-site healthy studies. So that is our motivations. And there are some previous works on this topic. The term proposed a probabilistic method which based on the Bloom filter, which can securely link the data from the two parties. But the problem is that method requires the semi-honest third party. And the core have proposed a seeding hash method, which can also protect the attack against the external party. But we know that the hash method may be vulnerable for the collision attacks. So the hackers may easily create the collision payloads with the hash method being published. And the Lazary proposed an idea privacy preserving recall linkage based on the homomorphic encryption. We know that the homomorphic encryption is the technique that is based on the ciphertext. They can perform many operations directly on the ciphertext, which do not require to decrypt the ciphertext. But this method also requires a semi-honest third party, so that cannot guarantee the whole picture of the security. So here in our project, we tend to propose the idea which contains two parties, and there is no other parties engaged into the in the data linkage process. So here is our basic scheme. This is a secure two-party patient recall linkage models. And during this model, we can see that there are only two interactors, and no extra information is revealed to the two parties beyond the results of the matching. So that means that during the interactively link process, each party does not know any information about the others. Although more importantly is that this model just needs only two interactors, does not require another other third party to engage into the secure interactive linkage process. Here is a comparison about some different security frameworks which can support us the techniques we can use to build our two-party models. The first is I have mentioned the homomorphic encryption. We know I have mentioned that this method can directly make some operations over the ciphertext, not required to decrypt the text. But this method have some problem. One is that the performance is challenging to handle some complicated functions, and this method may also require a semi-honest third party. And for the another one is the GMW method. The GMW method is a multi-party computing technique which is based on the secret sharing scheme. And this method is proposed by 3 researchers, and the name is the ability for the initials. And these problems also have some problems when the data set scales up. So here the gobble circuit one is a secure two-party protocols, and this protocol may have relatively efficient performance compared to the other frameworks. But when we use this technique, we may have to design dedicated circuit for each specific tasks. So here I will briefly introduce how the gobble circuit works and why it can securely evaluate, compute some functions. So the gobble circuit is also called the Yao semi-honest protocol. It's proposed by Dr. Yao, and this technique can compare any two-party functions fx and y securely, where the two parameters x and y come from the two different parties. So when we want to do the secure computing, we need to firstly convert the mathematical function f into some combinations of the Boolean circuits, such as some combination of the XOR and or OR gates. So I will give simple examples here. So considering about this function, which is the fxa and xb, and when the x is equal to the b, it will return 1, otherwise return 0. So if we want to convert this function directly into some Boolean circuits, it can be designed at the bottom pictures, which combines two XOR gates and one OR gates. We can see that in here the party A is denotes the input for XA, and party B is denotes for the input for the XB. And we use the double 0 indicate the input 0, and the 0 and 1 indicate the input 1. So here we can see when the party A's input is 0, it will firstly into the XOR gates. We can see the down there is a truth table, and we search for the truth table. We can know the output is 0, and we continually evaluate all the gates. We will have the results for the circuit, which is 1. That indicates that when the x is equal to 0 and b is equal to 1, the total output is 1, and it's exactly what we want to do for the mathematical function. So here is a simple example for how to convert the mathematical function into a Boolean circuit. So after we have already converted it to the combination of some Boolean circuits, now we can go through how it works during the secure evaluation. Firstly, the party A will generate the gobbled circuits corresponding to the previously circuits we have already converted, and gobble all the inputs by the gobbled values. We can see there are the case in these circuits, and that is a simple mapping scheme designed by A. So the party B do not know how the party A designed the mapping schemes. That means the party B knows nothing about the A, how they design the gobbled circuits. And in the next stage, the party B will retrieve all these gobbled circuits from party A, because the party A will create the circuits taking account to all the potential inputs for party B. So the party B can retrieve these circuits from party A, but party B will only evaluate the gobbled circuit by its own inputs. Thanks to the oblivious transfer, the party A can know nothing about the party B, since the party B will retrieve specific inputs without the party A knowing what the input exactly is. So after the party B have the inputs and the gobbled circuit, it will securely evaluate the gobbled circuit and have the computing results. So during this protocol and this flow, we can see that by doing this, the two interactors can interactively compute the results without any other parties knowing their inputs. And more importantly is that this scheme only have two interactors and do not require any other third parties in this computing process. So here is what we have implemented the patient recall linkage based on the GC method, and we use the FlexSA, which is a Java library, already contains many basic gobbled circuit functions like the addition, multiplication, and the comparison. So based on these basic circuits, we can easily construct the recall matching algorithm. And then we will have these slides have some experiments information about our experiment on the gobbled circuit patient linkage method. Our platform is programmed by the Java language, and we will assign two data sets. Firstly, to a CSV data both contains the 10,000 records. And we will use two threads to simulate the two parties and perform secure computing within the two parties. Here is the four rules for the matching records. And we assign a weight for each record. And if for each rules, and if two records are equal under one rules, we will add the weight to the overall score. And the fifth rule is how the score is computed. We can see that in this case, the lowercase r indicate the rules, and uppercase r is the record. And for the W here is indicate the corresponding weight for the rule. And after we have the overall score, we will compare to the threshold, and to decide whether the two records have been linked or not. So here is a basic scheme and experiment setup for our experiment. But if we directly do the things, if we directly do the computing, we will have some performance problems. So we can consider these things. If the party A have M records, the party B have N records, the computational complexity is OMN. So it is a very high computing complexity. But we have proposed an idea which can filter all the irrelevant linkage, but just concentrate on some small set of the linkage. So what we have to do is, instead of comparing the whole rules, we only compare the part of hash on the double circuit for each rule. And we will only consider the potential match linkage if at least one of these part hashes are equal for both records, and discard the linkage if none of these part hashes are equal. So by doing that, we can reduce the whole linkage space down to a very small scale. And we will briefly show the results here. We can see that all the double circuit result may take 57 hours, but by doing our method, it will be reduced to 5 hours, and the 5 hours is acceptable for most applications, most healthy record applications. And we see that even if the hash method may hit the fastest speed, but I have recalled that the hash method is not secure, and the double circuit can protect a much higher level of the security. So here is the comparison about our method and double circuit. And the GC can provide more secure computing and more secure operations. And even if the GC may run slower, but the hash method, but the runtime is still acceptable. So here is some conclusion. We can know that the double circuit we proposed can securely link two parties, and also the performance evaluation indicate the runtime is acceptable. More importantly, the GC can be easily extended to the multi-party. And here I will briefly, I will skip the extended work for our project, because this is extended work for our project to extend the two-party to the three-party. And in the future work, we can see that in our method, the GC method may suffer from the performance overhead. So in the next stage, we may concentrate on how to speed up our performance. The best idea may be the hardwire technique, like the crossbar or FPGA, which can significantly speed up the computing speed and subsequently improve the performance for the secure patient record linkage. So here I also want to thank my mentors, Dr. Wang, Dr. Chen, and Dr. Jiang, and all professors here, professor staff and interns, iDASH, DBMI, and NIH. Thank you, everyone. Thanks.
Hello? Okay. Hello, everyone. Our project is the privacy preserving genomic data outsourcing. And my name is, okay. My name is Wei Jia, and this is my teammate Tianyi. We both are the undergraduate volunteer in this intern program, and we come from Department of Automation, Tsinghua University. We are working with Dr. Chen, Dr. Wang, and Dr. Jiang. And first of all, as we know, this is our outline of our today's presentation. We divide into two parts, and I will introduce the motivation and the background, and then discuss about our framework in this project. And then Tianyi will discuss about the secure data storage outsourcing, and then draw the conclusion and give the future work. And first of all, as we know, with the development of technology, the cost of obtaining human genomic data goes down. And today, the price is less than $1,000. And it means that the genomic data are becoming increasingly available, and it has the potential to advance public health and promote personalized medicine. However, the genomic data are also very sensitive. For example, an attacker can re-identify individual just use his genomic data. In 2013, the science paper shows that the Y chromosome can be used to recover an individual's surname. And what's more, the hacker can also get the predisposition of to some certain disease like diabetes, cancer, and also the information of genomic data is shared among blood relatives. It means that if the disclosure of an individual's genomic data can put his whole family at risk. So we want to solve this problem. That is the secure genomic data outsourcing. And first of all, we want to do is to solve the secure problem. That is the secure computation do. And here it is several secure data computation solutions. The first one is the software-based secure computation, including the homomorphic encryption and the secure multi-party computation using garbled circuit or secret sharing. But all these software-based secure computation suffer from scalability issue in handling large-scale genomic data. And this has been introduced by Chen Hong in the previous presentation. And we will directly introduce the second one. It is the hardware and software hybrid secure computation. And in this project, we are exploring the possibility of to do the secure and efficient data outsourcing use this solution. And here in this project, we are using the Intel software guard extension, which is a hardware-software hybrid solution, and to achieve the trustworthy job. And most of the significant features that it can create a hardware protected model. We call it enclave. And in the enclave, the data could not be accessed outside in the software, even though the operating system. Here is the example. In the normal application, the compromised privileged operating system can easily attack the memory and get back the data. But in the SGS protected application, this application will first create an enclave and then execute the code inside it. And in this situation, even though the operating system could not attack the enclave successfully and get the data, so the data in the enclave will be very safe. So here is a comparison among among several secure computation, including the homomorphic encryption, global circuit, secret sharing, and SGS. We can see from this table that SGS offer a much better performance in the terms of the capacity, storage, communication, and flexibility. So we want to use the SGS to do the secure and efficient data outsourcing. And here is the two use cases. First is the secure computation outsourcing. We do want to calculate the Hamming distance to measure the difference between two gene regions. This is helpful in the medical research. And then, since the genomic data is very large, so we want to do the secure storage outsourcing. And here, we adopt this algorithm to compress the data, because this algorithm it can render access over compressed data. It is very essential in the data access of the genomic data. And then it has another advantage is that it has higher compression ratio with less running time. Here is another table about this compressed algorithm. We can see that this has a higher compression ratio than others. Okay, and then here I will show you an example of what the data outsourcing do. First, the clients will send his encrypted this data to the server, and in the server, in the SGX enabled server, you will first create an enclave, and inside the enclave, since the data is very large, so we will first storage data, use the data theory, and then if we want to analyze any gene region of the genomic data, we can very easily to get the data and then use this algorithm to get the data without decompress all the genomic data. And then in the last steps, we can calculate the Hamming distance and then send back the result to the clients. Since all these steps are done in the enclave, so this will be very safe. Here is our experimental setups, because we want to test this framework and to show its performance. From the Windows Edition processor, installed memory, and our data come from the 1000 Genome project. Here is our experimental results. We first compare certain region gene in the chromosome 21 between the individual from the South Han Chinese with the African Caribbean individual. And then we measuring the time, the running time in each key step. And then in addition, we also compare the difference between the same races, like the Puerto Rican. And first, we can have a look at the first result is the Hamming distance. We can see that our output with SGX service is the same as the output with the non-SGX service. And then here, the distance between the two different races is really larger than from the same races. So our algorithm can really work. And all these steps is work in the enclave, so it is very safe. And then is the compression algorithm. We can see from this table that this file size is almost 10 times smaller than the same file size. It means that you can save about 90% of the hard disk space. This is very essential in the secured in the genomic data computation. And then this is the running time of our project. You can see that with the SGX service, with the time is just 10% over than with the plain text. In the result, we can see that our framework is both secure and efficient in data outsourcing with less space occupation. And later, my teammate will introduce about the data theory.
Well, hi. I am Tianyi Zhu from Department of Automation, Tsinghua University. I'm from China, and I do part of this project mainly about the data sealing part, and I do some introduces. And first, let's talk about why we need to seal data in SGX. First is about the secure hardware-based data outsourcing. And this kind of method, it's much faster than the software-based cryptographic computation. And second way is that we combine with the Intel SGX, we solve the problem between the encryption and computation. As we all know, sometimes when we do the encryption, we cannot do the computation anymore. And if we want to do the computation, we need to decrypt them. And it's very easy to be hacked and be stolen by any hackers. And second thing is about the memory problem. This picture shows you the different size between a typical Intel SGX enclave space size and a typical compressed data file size. And you can see that it's really large, much bigger than the enclave size. And so we need to split data file into some small pieces and save them outside the enclave into some, untrusted memory or to some disk of the server. So, and third thing is about the save and reuse. Well, as I said before, this genomic data file is very big. It's huge, and so we don't want the client to send the data to the server for too much time. So we want to save them outside our enclave, like on the server, and so that we can reuse them. And we save them and reuse them for some day later, maybe. So when you want to save them, some problem will arise. I will introduce you to typical attack, that's replay attack from the hackers. One is about the space attack. On the picture, it shows you two different space attacks that the hackers might do. First is about replacing the whole data. I mean, like replace his data part to him and send the fake one to our program, so that our program will not recognize that who you are sending to me and just do some analyzing and return you the fake result, and the client will receive the fake result and assume that was mine. And the second way is to, as I said before, when the data file is too big, so we need to split them into small pieces, and so the hackers can easily replace part of the data and send the whole thing to our program. At the same, our program will not recognize that who you are sending to me and just do the analyzing and return the fake result. And yes, the second kind of those replay attacks is about the time. As we can see, the data pack can be updated after several read or several write. And so the hackers, they can save the old version of the data part and just replace the new version and into the old data part and just send the old data part to our program, to our enclave. And also, as I said, the enclave will not recognize that what you are sending to me and just do the analyzing and return you the fake result. So how to protect this? This is what the Intel SGX do. Well, the Intel used the AES GCM, that's Advanced Encryption Standard, and Gauss counter mode encryption to protect the secret data, and so that any change on each data part will not be accepted using a MAC, that's Message Authentication Code. I will talk about that later. First, let's talk about the AES. What is AES? Well, it's a specification for the encryption of electronic data. It's established by the U.S. National Institute of Standards and Technology, that's NIST, in 2001. And also, the AES is the first and the only publicly accessible cipher approved by the National Security Agency, that's NSA, for the top secret information when using a NSA-approved cryptographic module. And the performance of the AES GCM in the Intel CPU has a 10 gigabytes per second throughput hardware instruction building with the Intel CPU. And also about the MAC, that's, I said before, the Message Authentication Code protects, this value protects both the message data's integrity as well as its authenticity by allowing the verifiers who also possess the secret key to detect any changes on to the message content. And also, Intel has two kind of policy to protect the attack that I said before. First is called the time-based policy. So on the picture shows you how the time-based policy works. That is, the data pack itself will be expired after a certain time duration. On the picture shows you that a trusted time source based in the SGX that helps the program to determine whether a data pack expired or not. That means the data pack cannot be used after the certain time duration, so that the hackers, even if they stole the data pack, they cannot reuse it. They cannot send the expired data pack to you. And the second way of policy protection is called the replay protect policy. That is, the data will be updated after each read or write, and so that the old version will not be accepted. That is, our program will keep the counter for each data pack, and also we will add a counter into each data pack and seal them outside our enclave, so that when you try to read a data pack, you may check the counter in the data pack, and also you may check the counter in your program, in your trusted memory, and you compare them. If they are not in the same number, that means that some old data pack has been replaced and send the old one to you. So also this kind of counter will be expired after a release version. So these two kind of policy will protect the data from the replacement attack. But a problem will come. That is the time complexity. Well, the replay protection policy and the time-based policy need to call the Intel platform service. And as we test, it really takes a very long time to call those functions. And this picture shows you the difference between the AES GCM encryption only encryption and the additional policy encryption. And it takes about less than a quarter second for a 10 megabyte file if we use the encryption, AES GCM encryption only. And if we add some policy inside, it takes about 1,000 seconds for a 10 megabyte file. You can't wait that long for a data sealing and unsealing. So, and also I want to say we split data into 1,000 bytes pieces for a better performance on data decompressing and analyzing. So what are we going to do? It's really take too long time. So we found out that our data is read only. So that means the client's data will only be for read, so that our program will have no version updated. So what we're going to do is we just focus on the replacement attack that's on the space. First, as I said before, this one kind of replacement is that the hackers, they try to swap two people's data and send the fake one to the program if you cannot know the identity of the data pack. And the second way is that the hackers may try to swap two parts of the data if no index information is sealed with original data. So you're not going to know which part you're reading. So this is what we do. We add something to the data. We add an index that makes sure you are reading the expecting part of data, and we add a user's ID, that is to verify the identity of the specific person. So this picture shows how our program works. Assume that you are trying to read the Bob's number 3 data part, and you read the hackers let you read the first part of the Bob, and you will have a wrong index, so that your reading will be failed. And the second way, you are reading the number 3 data part of the Alice. Well, you have a failed reading because our program will tell you that you have a wrong identity. So it's the only way you have a successful reading is that you are really reading the number 3 part of the Bob. So this kind of protection helps you to ensure that you are reading the expecting thing that. Yes, you're reading the expecting thing. So this is the space cost and the time cost of our program. Well, on the left picture shows the space cost, the line above. It takes about 1,700 megabytes for a 1,000 megabyte file. And on the right picture shows the time cost. It takes about 20 seconds for a 1,000 megabyte file. And the picture on the left, the line below shows that if we use the AES GCM only, space cost. It's about 1,500 megabyte file. So we add about 200 megabytes file for our policy, and we do reduce many times on the protection. So now I will give you the summary and the future directions of our whole project. And first is about a summary. Our platform based on the Intel SGX can provide a security guarantee when privileged health component is potentially malicious. And also the hardware support provides our platform significant performance increment compared with some traditional methods. And also we enable the dynamic data storage and computation outsourcing. And also we have some future works. First, we want to support the Linux platform because now it's on the Windows. And also we want to support more dynamic data analysis tasks. Now it's just the Hamming distance. And at last, we have some acknowledgments. Thanks to our mentor, Dr. Chen, Dr. Jiang, and Dr. Wang. And also thanks to all the professors, staffs, and interns, iDASH, DBMI, and NIH. Thank you. And yes, the question time.
Hi, my name is Jonathan Wicks, and I'm a UCSD bioengineering undergraduate. And I'm here to talk about mapping clinical genetic data to the HL7 biomedical standards. Here's my project team. I worked under Olivier Harris-Mendy and Hyun-Hee Kim, along with Wendy Zhu, Lisa Menlensky, and Hyundai Kim. So the current state of the clinical data warehouse is that there's no way of encoding genetic information into the medical records. Right now, the reports are scanned through a PDF and uploaded into the EPIC database, which makes it very hard to parse through as the data itself is not encoded in and is instead referenced as a file name or either a true or false statement whether an individual has mutations. So for this project, we wanted to receive more machine-readable XML formatted data and import that into the clinical data warehouse and allow that, essentially allow researchers and clinicians to easily sort through and select data for research. We decided to look at our standards in HL7 as they're currently developing a new generic standard. They just updated their entire coding system for under LOINC this past June. And by using HL7, we easily able to encode into other medical standards for more like messaging use or other just standard medical use. So HL7 actually uses a variety of different nomenclatures and standards for recording their genetic data. Specifically, they use the Human Genome Variation Society's standards for recording the names of mutations, the Heterogene Nomenclature Committee for recording the names of genes, and an overall LOINC structure for categorizing data and essentially classifying types of the genetic mutations. So here's an example of of a translation from a medical or a medical report into this new standard. For the first patient, we have a mutation in the KRAS gene or a missense mutation in the KRAS gene, and you can see that in the lower table, it's translated down into an HGVS nomenclature for the mutation, the heterogene name for the genome itself, and we changed the mutation type to a LOINC code with the structural code for the LOINC right next to it. But HL7 actually has a wide variety of these categories for both DNA and DNA, RNA, and amino acid changes. So all these are codable and are able to be reported consistently and allowing easy categorization. So we actually wanted to apply this to a large data set. We received data from Foundation Medicine from over the course of 5 years from 1,700 patients. And these samples are from tumor cells, or they essentially sample from tumor cells to find cancer-causing mutations. And they use the Foundation 1 genomic profile. And this sequences a whole genome from 350 genes and introns from 28 other ones. And it's very important that this is focused on finding somatic mutations rather than germline mutations, where somatic is essentially more likely to be a cause of the tumor. And they also record extra information such as equivocal and subclonal information, which is based off the somatic mutation. So here's an example of the report. As you can see, there's some blocked out patient information on top with the mutations at the very bottom. So this individual has 3 different mutations: amplification in the RAF1 gene, another amplification in MYC, and a missense mutation in the TP53 gene. But one of the issues with Foundation Medicine is that they've been developing this standard over the course of this 5 years. So they're consistently changing the way they report these mutations, and overall don't have a necessarily structured way of reporting. They record information about the variants of known and unknown significance. So this signifies whether there's a knowledgeable background for a variant, and include, like I said before, include information on subclonal and equivocal. So one of the important aspects of looking at HL7 and looking at this Foundation Medicine data is the difference between germline mutations and somatic mutations. From looking at the HL7 standards, we can see that it was probably built for more use under the germline mutations, as they require more consistent nomenclature and they're much easier to report. The somatic mutations, on the other hand, are only present in a subset of cells, and therefore, and because of the nature of the tumor cells, the chromosomal instability leads to more non-standard types of mutations, which is not recorded in HGVS or any of the Wnt structures yet. So this causes issues with mutations like fusions, rearrangements, and chromosomal loss, as there's some changes in just the overall way that you report it in terms of somatic versus germline. And in addition, there's information such as this subclonal and equivocal information under the somatic data, where subclonal is essentially only present in a small subset of the tumor, and equivocal has to do more with a very specific aspect of the copy number alterations for amplification and loss. But what we can do is we can still look at this data from Foundation Medicine and infer the different standard nomenclatures. So what I worked on was essentially parsing through this information and changing the way they report the gene name into the proper HGNC gene symbol. There's a variety of variant names into the HGVS notation and the variant types, which is actually one of the hardest parts of this project, and essentially mapping specimen site and diagnosis to their given standards for SNOMED CT and ICD-10. So going on for the inconsistencies in nomenclature, you can see that the more common mutations such as missense, frameshift, and amplification are actually able to be recorded under a code, while the more Foundation Medicine specific or somatic specific does not have a codable structure yet, such as splice, exon deletion, and fusion. And so these alterations are reported by Foundation Medicine, and they do still have clinical significance. However, there's no standard for HGVS or no standard under Wnt. So if we look at the first 2 examples, they use a very specific notation with which can either indicate an insertion or deletion, or an insertion deletion, which creates some ambiguity in the way it's reported. They report things like fusion and truncation, which isn't actually part of HGVS or Wnt. And there's the ambiguity in the exon and intron data, because the ambiguity and precision for recording these are mutations. So for our solution, we created our temporary local codes for these different types of mutations, and essentially are waiting for these standards to be updated to include them. So if we look, we can see that at least for the majority of data, however, there is a codable structure to it. So all the green mutations are codable, while all the red ones are not. And there's only around 7% which we haven't been able to code, and that's specific to this ambiguous exon and intron mutations, along with some more specific structural mutations. So another issue that we have is reporting the subclonal and equivocal data, as it's more specific to the Foundation Medicine data set itself. However, it's still important for finding the causes of tumor and for clinical significance. But since right now there's no way of actually coding it into the HL7 system, we decided to leave it out. But it can still be included later on if they decide to update their nomenclature. And lastly, there's the issue of reporting the variant of unknown significance, where in Foundation Medicine, they either report this as a binary true or false, where they just signify 1 for unknown, 0 for known, while the Wnt structure that HL7 developed is actually more of a general clinical significance from pathogenic to benign. So right now we're encoding only the VUS mutations and rather leaving the non-VUS as a non-coded data set, because we can't necessarily infer what is pathogenic or benign unless we essentially apply this against a annotation database. So our future plans is to work on importing more alteration data from other companies and forming a pipeline so this data can automatically be parsed into the clinical data warehouse. And this will essentially allow both companies and researchers to easily import this data and possibly just create a streamline to immediately put this in rather than having to worry about parsing through these individual files or looking at individual patients at first. I'd like to thank my mentor, Olivia Harris-Mendy, and working under Hyunhae Kim, with collaborators Foundation Medicine, all professors, staff, and interns, iDASH, DBMI, UC Rex, NIH, and the CTRI iDASH team. Thank you.
Next speaker, and welcome the next speaker, Lee from Emory University. And she's presentation is about distributed learning from multiple EHR databases for a contextual embedded model for medical image.
Hi everyone, the topic I'm going to present today is called Distributed Learning from Multiple EHR Databases, Contextual Embedding Models for Medical Events. And this project is mentored by Dr. Xiaoqian Jiang, and I'm Zili from Emory University. So to motivate our problem, suppose that I know 2 researchers, Dr. X and Dr. Y, and each of them have access to one EHR databases. They want to collaborate to build a global model, but they don't want to share the data. So how can they solve this problem? So this is the goal of our project. We want to, based on the previous work, develop a system which can learn from multiple databases. Also, we want to make predictions for new patients. So the structure of my presentation is laid out here. I will first give some background, then describe in detail the 3 methods we proposed. Then I will demonstrate you some preliminary results and end in conclusion and discussion. So a little background about the tool we use. It's called Word2Vec. It's proposed by some Google researchers in 2013. And it can obtain vector representation for words after training. So suppose this model, Word2Vec model is here, and it has been trained. By using this model, I can obtain the n-dimensional vector representation for each word. And there's a very nice property of this Word2Vec, is that the vector learned by Word2Vec have some contextual meaning. In this example, the vector of Madrid minus the vector of Spain plus vector of France is actually equal to the vector of Paris. So the word2vec can actually learn to understand the meaning of each word and generated the vector representation for that. The basic structure of word2vec is on a 3-layer neural network, and it has 2 model structure. The first is called skipgram, and the second is the continuous bag of word. And the skipgram model uses 1 word in the context as the input, and all the contextual words around that word as the output, and the continuous bag of words are the other way around. So they are just 2 different model formulations, but will give you very similar results. Another background is about this PDPS model, Patient Diagnosis Projection Similarity Model. It is proposed by Dr. Jiang's group very recently, and this model can build a prediction for patients' medical events based on word2vec, and it can achieve a pretty good predictive performance. So even if the current method can solve the problem very well, but it can only learn from 1 database. And there are many benefits of learning from multiple databases. For example, you will be able to obtain more data, and you will be able to achieve a better performing accuracy. But there are also many technical difficulties of learning from multiple databases. The first is usually the EHR data, they are very big, they are large-scale data, and it's kind of hard to transfer and to storage all the data in 1 single place. Also, their privacy issue is always a big concern. So here we propose three models to save this problem. The first is called naive update. I assume there are 2 data sets, D1 and D2. I first trained the model using the first data set. It's called naive updates because it's the most straightforward and simple method. We just expand the vocabulary of the first model and add new nodes into the input layer and output layer. Okay. And then we train the expanded model using the new data set. So it's very easy, but it does not guarantee we'll have the same results as the global model, where you train the model using all the data set. The second method we propose is called dropout updates. It's called dropout because it comes from the idea in your network. Dropout is usually used in your network to avoid overfitting. We also use the idea here. So in each iteration, we select a subset of new nodes and add the new node to the existing model. Then we repeat this process several times and average the vector representation over all the trained model to get a final result. So this idea comes out because we think the difference between the new model with the global model is that the new node which is added to that. So we want to minimize the new node. That's why we only select a subset of the new nodes. The last method we propose is called distributed NCE, noise contrastive estimation. Again, assume I have 2 data sets, D1 and D2. I first obtain the raw vocabulary from D1 and D2, then I merge the 2 vocabulary. I use this 2 vocabulary to build a global model in the middle, and I train the global model sequentially. First, I train it using the database 1 and database 2. All these 3 methods does not require the multiple or 2 data sets to be stored in the same place. The analysis can be done on site, and there's no private. There might be a very little privacy thing involved. Also, it can be naturally extended to 3 data sets or more than 3 data sets. So we conducted a simulation study to examine our method. We use a data set is called MIMIC3 data set, which is real data obtaining from the Beth Israel Hospital, the ICU department of Boston. And we designed 3 scenarios. We first separate the data set to 90% as training and 10% as testing. And in each scenario, we manually separate the training set into equal size, 45%, 45%, or unequal size. And the two criteria we use to examine our method, the first is called precision top K, or PTK. It's like if you give me a word, I can find K most similar words to it by two different methods. Then I compare these two lists and find how many of them are overlapped. So PTK can tell us how good the structure is maintained by the new method. The second criterion is called the average area under curve, average AUC, which is a very traditional index for measuring the prediction power. So here come some preliminary results. So the first line is the result of naive updates, then the dropout updates, distributed NCE, and the last line is our global model, which we think is like our golden standard. So for these two criteria I mentioned, we want them to be as large as the larger, the better. So a high value means a better performance. So I want to point out three things. The first is we found that PTK is a more sensitive criteria than average AUC. So you can see that PTK can range from 20% to 70%. The second thing I want to point out is PTK is consistent with average AUC. For example, dropout updates have low PTK. It also have a lower average AUC. The last thing I want to say is this distributed NCE actually performs the best among all the three proposed methods, and the result is very close to the global model. This plot, the x-axis is the K selection, and the y-axis is the PTK. So we found that the top line, or the blue line, is a global model, and the purple line is a distributed NCE model, and green line is naive updates, and red line is dropout updates. We found that for each selection of K, the distributed NCE performs the best and is more closer to the global model than the other methods. So for some future work, we want to further improve the performance of distributed NCE. In our thinking is that a distributed NCE should be very close or almost the same results as the global model, so we want to further improve it. Then we want to add some privacy protection to the current methods. Last, we want to, if possible, we want to try our method on the UCSD data to further examine the performance. I want to give my final acknowledgement to my mentor, Dr. Xiaoqian Jiang, and to our collaborator, Dr. Qilong from Emory University. I want to thank all professors and staff and interns, and iDASH and DBMI, and thank NIH for the great support of this work. Thank you.
So our master speaker will be Victoria No from UC Davis, and the presentation is about designing a community-based chronic disease self-management program with informatics strategy.
Hello. Hi, everybody. How is everybody doing this morning? Great. I don't know if it's better to be the last speaker or the first speaker, because I know I'm standing in between you and lunch, so I'm going to try to speed this up and share a little bit of what I'm going to be talking about today. So I'll be talking about designing a community-based chronic disease self-management program with an informatics strategy. And my name is Victoria No. I am a second-year PhD student from UC Davis Betty Irene Moore School of Nursing. And my mentors this summer are Dr. Hyunhee Kim and Xiaoqian Jiang. So chronic disease. Does anybody know what a chronic disease is? Okay, never mind. So chronic disease is a disease that lasts for a long time. So according to the U.S. Center for National Health Statistics, it's a disease that lasts 3 months or longer, right? So examples, any common examples of chronic diseases? I will tell you. Heart disease, stroke, cancer, diabetes, obesity, and arthritis. So I put these chronic diseases up because they're the most common, and also it costs the U.S. health system a lot of money for direct and indirect care. And as well, the complications associated with these chronic diseases are often preventable. So the prevalence of chronic disease, there are about 117 million adults living with chronic disease right now, and it is the leading cause of death and disability in the United States. And you're thinking 117 million people. Is that a lot? Yes, that's 1 in 2 adults in the United States. So the cost, it costs 86% of all healthcare spending in 2010. So for people with chronic conditions, and that's a lot, because when you're talking about healthcare spending in the United States, that's $2.6 trillion, right? So that's a lot of zeros at the end. So if you break it down, you're seeing that people are living with more than one chronic condition. So people don't have just 1, 2, 3. The majority of people who have chronic conditions live with 5 or more chronic conditions. So you have diabetes, hypertension, cancer, all these other things, arthritis. So my interest is really in community health, and the terminology of community health is very broad in public health and in research, and it draws upon diverse disciplines and expertise. And I'm also interested in self-management within the community health aspect of care. So we realize that the majority of care happens outside of the clinical setting. I think a lot of times when we work in the hospital setting or in the medical setting, we're thinking, oh, we have to work about our patient visits, and it's happening all inside the setting. And the reality is that people go beyond that 15 minutes. What happens is that people are taking care of themselves, taking medication, exercising, doing self-management and other things related to their health, and it's not in the clinical setting. And behavior change, when you're talking about taking care of your chronic disease, it's hard, right? So behavior change is difficult, and self-management, when you're talking about that terminology, it takes more than just yourself, right? It takes a team to take care of these people. So the purpose of the iDASH internship, so if you look at the acronym of iDASH, it stands for Integrating Data for Analysis, Anonymization, and Sharing. So my goal was really to learn from an interdisciplinary group of biomedical informaticists, computer scientists, data analysts, and clinicians, and hopefully be able to contribute to new and emerging research as a team, and also take the knowledge that I've learned here today at UCSD and then bring it back so that I can contribute to future projects. So I'm also very interested in translational research. So when we're talking about translational research, it's a very highly interdisciplinary field. And most people know about translational research as bench to bedside research. And what it is, it's when you're taking basic research and it gets translated into clinical research. What I'm really interested in is the translation into clinical practice. And then hopefully the knowledge that we get from clinical practice will translate and also inform further research for basic research in the future. So as a researcher, since I'm in my second year of PhD program, I really want to learn about how to lead research as a whole. So from the conception, the design, implementation, evaluation, dissemination. I think these are the key factors in terms of how I would like to make an impact. And the reality in community healthcare is that the evidence base is actually very limited, right? So the absence of consensus of the definition of the scope target community. So when you're a researcher, you're thinking of community as multiple definitions, right? So community can be a setting, it can be a target, it can be a resource, it can be an agent. So when you're actually looking for data around what this community research is, it's very, very difficult. And there's a lot of complexity if you're actually working in the community as well, right? And clean scientific methods, especially when you're actually doing experimentation and intervention in the community, is very, very difficult. And that doesn't come without any reason, right? Part of the thing is that we have to build relationships as researchers with the community. There's the whole institute that just recently came out with the Patient-Centered Outcomes Research Institute, which UCSD is one of the leading researchers in this. And you're really including the patient as part of your research. And part of this is really related to trust, right? So where is this trust coming from? So just giving you a historical perspective, you guys are probably familiar with the Tuskegee syphilis study in the 30s, and the Native American uranium mining in the 40s and 50s is Henrietta Lacks. Are you guys familiar with these different research studies where there's not that much information being passed when research is being done? So the two intern projects that I was participating in this summer was the Committed project, which Hannah graciously presented. It was very, very nice. And the iDASH, which Ted presented. And so my contributions for these two particular projects was really focused around how can we actually provide consumer health application to it, provide interventional design in the future if we decide to do an intervention with these two technologies, research evaluation, as well as proposal development in the future. So this is a great opportunity because it's a very highly interdisciplinary field. So this is our team. So I'll be talking about this, you've heard about the proof of concept study. So I'll talk about our team roles and the contributions that I've given. So the roles were Dr. Hyunhee Kim was our PI. And for Committed, Hannah was our project manager. She did a lot of great job organizing all of us, making sure that we were on track, and literature reviews and like basic programming, right, Hannah? We were just learning all of that, and it was really fun. And we had programmers, Vincent Yao and Alex Richardson, really providing creating the database, providing the web applications, and it was very, very interesting. And for me, I was part of the user and research design of this aspect, so I helped contribute in the sense that, actually, I'll talk a little bit about that more. So I really wanted to introduce this animation. I wasn't sure earlier, but that's our PI, and Hannah was our project manager. Vincent and Alex were our programmers, and that's me, and together we make a 5-star team. That's why I was a little joke there. So part of my contributions was really to provide the systematic literature review methodology. So Hannah mentioned earlier about the Cochrane Review's grade approach in terms of evaluating the strength of evidence. And I also participate in the user interface design as well. So the implications for Committed, Hannah touched upon it, but I wanted to talk about what it means to be facilitating patient and provider communication, right? So that's very, very difficult, especially in the research world. And also in the patient-provider world, right? How do we measure communication? How do we actually improve patient and provider communication as a whole? And hopefully with this particular technology, we'd be able to do that. And it's really, really exciting because most recently I worked on a community project in Oakland, California, where we're looking at health-seeking behavior, right? And we're looking at how we can actually look up evidence-based health information. It was very, very difficult, other than you going to Dr. Google and looking for that information. And this is the most difficult part. When you're talking about connecting research findings with evidence-based recommendations, I think that's the hardest thing to do. And right now, with all this data being available, how do you synthesize that data and figure out, this is the best recommendation for us now? The next project is iDASH, and aside from Dr. Kim being a great researcher, she's so good at coming up with acronyms for the names for our research projects. So just to introduce our team, she was our PI as well, project manager and programmer, Ted, because Ted made sure I said that he was a programmer as well. And Ming was also a programmer, and I helped with user testing and research. And together we're 4 points. I would say we're an A team. 4.0. So my contribution to this particular project was on literature review on stress evaluation. So we looked at heart rate variability. We looked at different research methodology out there. User testing, as you can see, I was wearing this all the time. I think some people thought it was a fashion item. I don't know if it looked really good or not, but it was there. And I was part of the verification, validation, and comparison of the devices. So here on the left side is me wearing my iWatch, and then on the right side is me wearing the actual Microsoft band. So implications, right? So when we're talking about stress, and so I've worked in hospital administration for quite a number of years, right? Facilitation and teamwork and support is very, very important, right? So when we're talking about, okay, productivity, how do we get this done, and you're working in a team setting, and different people have different ideas of what it is, I think that's going to be very difficult when we're talking about creating opportunities for mindful discussions, right? So intentions of having the ability to have these mindful discussions is very, very important. Because, you know, at the end of the day, the implications is that we want a healthier workforce. We want a more happier workforce. We want a more productive workforce. So in bringing back my talk and bringing back all the things that I've learned this summer, I wanted to talk about like how I can design a self-management program using an informatics strategy, right? So the first part is when you're defining a problem and you're inviting stakeholders to come to the table to figure out how to solve this problem and developing a solution and designing an intervention, defining evaluation parameters and creating an implementation plan, where does that fit in? Where does informatics fit in? Or especially when you're also implementing and evaluating. Can anybody tell me? Trick question. Informatics plays a role in every step of the process. And I think a lot of times when people talk about evaluation, especially when I'm putting together teams in the research or in the clinical setting, we always think of informatics as maybe we'll do it in the evaluation phase. Oh, maybe we'll bring it at the end when we can't figure out the problem and how to get this data, right? So the idea is that if we include informaticists from the beginning, then we can actually figure out how to define these measures and measure like what success means in this research parameter. So the significance of this particular summer was really to see like how can I actually learn from everybody here and then actually apply it. So the reality is that we have an aging population in the US, right? So people are living longer. What are we going to do about this? And also healthcare is shifting from the inpatient to the outpatient setting. And what that means is there's more need and more requirements for providing better community care. And I don't know if you guys are familiar with the triple aim. This is Dr. Berwick's Institute on Healthcare Improvement. And when he talks about healthcare improvement, we're really looking at population health, experience of care, population health, and per capita costs, right? So in all these aspects of care, we're looking at how we can improve it. And as informaticists, we really have to find that data to actually make these decisions, how to make this better, right? And I felt like this summer was really great in the sense that I was able to also contribute to one more aim. And this is written by Tom Bodenheimer at UCSF when he talks about the quadruple aim, right? So we're not only talking about improved patient care, better health outcomes from a population perspective and lower costs. We're also talking about improved clinician care as a whole, right? So all these things that we're actually learning, even though these are proof of concept studies, the implications are very, very high. So in summary, what have I learned for the last few weeks? Data is valuable, but how you use the data makes research more impactful. And these are in my discussions when I was talking with Dr. Kim about this, right? So it's great that we have all this wonderful data out there, but how are we going to use this? How is this going to be impactful for the future? This is my favorite part of this internship when I was talking about frequent team discussions are critical. I see the PIs, Dr. Jiang and Dr. Kim, checking in with their interns, the interns checking in with each other, they running into meetings, but also having time to communicate. I think that's really valuable, especially in an interdisciplinary team. And finally, science should be open and data should be shared. And this is actually coming from something I read from Dr. Ono Machado, who's actually in the room right now. She mentioned this was, I read this in JAMIA earlier this year when she sent a message to the future biomedical informatics professionals. And we're talking about what data actually means and whether researchers in data are actually parasites. So when we're talking about that, it's true. I think people are curious about whether they should be sharing the data and whether science should be open. And the reality is that you have to if you want innovation to move forward. So thank you so much. I wanted to thank my mentors, Dr. Hyunhee Kim, Dr. Jang, and Dr. Kathy Kim, who's at UC Davis. Also would like to thank my collaborators, Hannah Kang, Ted Ochiai, Vincent Yao, Ming Dai, Alex Richardson, all professors and staff and interns, iDASH and DBMI and NIH. Thank you. These are my references. If you guys have any questions, let me know.
So if there's no more questions, I'll ask a quick closing remark. So we have a play hard and work hard environment. So we organize several events like the movie watching and kayak event. Also we have the birthday party for our interns. And for the research part, we have the input from the interns and our experienced mentors. And the output will be posters, object papers, our new tools, and the new knowledge, which give us a promising future of iDASH and biomedical informatics.
Okay, thanks everyone, and I hope you enjoy the summer, and I hope you bring the great memory home and send your friends or your colleagues, your classmates to our next intern. And we do have a lunch hosted in the different building at BRF 5A03 at 12:30. So hope you enjoy the rest of the day. Thank you all.